Good afternoon, everyone. Am I audible at the back? Middle? There's no one at the back. So I'll first show the questions which you put in the assignment. I hope everyone has at least taken a look, even if you've not started. So some of the questions, I'll give a lot of boilerplate code today itself, so that it's fairly easy for you to solve these assignments. I want to mainly just firstly walk over the questions. The first one is to implement logistic regression in Pyro. So this should be fairly straightforward given what we have already done. And the second one was the same data set that we've seen earlier, FVC data set. This was the problem which we studied in the Bayesian hierarchical networks. So a lot of the things which we are trying to do in the previous 3, 4, 5 set of lectures is when we don't have a lot of data in a target task, in a new task, in a target task. That is the broad framework. Sometimes people call that few shot learning, sometimes people can call it different kinds of names, but essentially that is what we're trying to solve when we don't have a lot of data in a target task. Now, whenever we don't have a lot of data in the target task, we can have various methods of solving it, and we've looked at it in the Bayesian hierarchical model problem statement. There we had a few models. One, we learned a single model for all the participants, all the patients, right? The other model was we learned a patient specific model. What was the downside of learning a patient specific model? You may not have a lot of data for some of the patients, plus you're not leveraging the models or the learning across the different patients, right? What is the downside of having learning a single model from all the patients? The model will not be able to capture the specifics of individual patients, right? So it may exhibit a very high bias, whereas the other one may exhibit a high amount of variance, right? So therefore we picked up something in between which we call partially pooled. In this question we are telling you to compare the different variants of poolings on a test set. The next question is, we want to be reproducing figure 4 from these papers, and we will be giving you, we've already given you some notebook, we will be giving you some more notebooks. So the essential idea in this kind of a problem setup is, we will be looking at image reconstruction, right? So given an image in an autoencoder like wave, if that's easy to understand, we want to reconstruct images. Given certain pixels in an image, given coordinates in an image, x, y, and their pixel values, can we predict the pixel values at unknown coordinates, right? So we formulate this problem as a regression task firstly. It may seem counterintuitive, why are you looking at images and talking about a regression task? So this is what it is. So we have a 2D image as in we have x, y as the two coordinates and the corresponding values, which is the grayscale value for this image. If we look at this x0 and x1, and we can then accordingly see that we can try and solve a regression problem around this. Given a new x0 and x1, we can predict its value, right? So this is broadly what we'll be doing in this assignment. We are given these 10 context points, which means that we are given just these 10 x, y and the corresponding pixel values, right? So this pixel seems to be white, this is some shade of black, etc., right? Given these 10 pixel values, I want to be able to generate what the image most likely is, right? Obviously, as we'll have more context points available or more points for which we know the true label, we'll be able to do a much better job at reconstruction, right? So the broad task is to regenerate or is to create images given a few context points available from those images, right? The way we are solving this problem is using something known as a coordinate network. A coordinate network converts the problem of the image problem into the input size where you have x value, x pixel value, x coordinate value, y coordinate value, and correspondingly the pixel value which we have. So a couple of papers have done this. One is the neural process paper which I had shown earlier, and similarly another paper which is called the SIREN paper. So you notice they have the similar kind of a plot, right? So given some kind of context, they're trying to inpaint or they're trying to complete the image. Of course, as the context size is increasing, they're seeing better reconstruction. They're also challenging you in different environments. They can also be giving you where the data is missing in a very structured way. In this case, the bottom half of the image is missing, right? Now, why do you think this task makes for an interesting task when we are talking about the few shot setting or the setting where we may not have a lot of data? Why are we studying this specific image in painting task? Okay, before that, can someone quickly summarize what a coordinate network might mean? I just discussed this a couple of minutes back.
Given the coordinates x0 and x1 in 2 dimensions for an image,
Okay.
to predict an intensity, and that conversion can be done by the network.
Right, right.
Mostly, like on the previous question you asked, the image in painting would usually have very few images in real world.
Of very few images in the real world, yes.
Particular context.
Right, right.
That's the reason we look at this image reconstruction with few shots.
Yeah, so we are trying to solve this as a few shot problem because the setting is fitting well. For any new task, if you have very few context points available, what can you predict for those tasks, right? At the same time, you may have a lot of data from some other task. You may have a lot of full images of, let's say, 20 celebs, but you don't have the 21st celeb. Or we have a lot of images for a few MNIST digits, but we have only a few context points for new MNIST digit. Can you complete that image? Right? So that's the broad problem statement. We'll be looking at solving this using this idea which is in this paper called SIREN. This again looks like a very sophisticated paper, but it turns out to be a very nice paper without a lot of complex things. Like we can at least quickly implement some of the things here. Right? So the idea that they're talking about is they are again looking at coordinate networks which convert the image firstly into coordinate input, right? So you get an input x, input y, and correspondingly for RGB images you will get 3 values. Right? And what they're showing is that if you use SIREN, if they use their proposed method which is called SIREN, which involves changing the activation to a sign, right? Instead of using ReLU as an activation, if you use a sign, then one, you see that the reconstruction is good, right? The reconstruction in the ReLU and the other networks. So ReLU one is a little hazy. TANH one is better, but still a little hazy. But the SIREN reconstruction looks to be very good. But more importantly, if you look at the gradient of the image, right, that what you're obtaining in the ground truth versus that what you're obtaining via SIREN is fairly good. The second gradient of the image, what for ReLU, is a blank image. Right? Why is that?
Second derivative power of, power 1 of x is 0.
So you have, if you have activation as ReLU, right? So you will have a first gradient which will be a constant, and after that the second gradient would be 0. So therefore you are not able to see anything here. Whereas with signs, how many times is a sign differentiable? Infinitely, right? So what they're saying is that through their proposed method, they are able to not only reconstruct the input image, but also they are able to very accurately capture the first and the second gradients. Right? In the image world, they call it with some specific names, like the Laplacian, etc. But that's essentially what this paper is talking about. And for most parts of the paper, they are mainly just talking about a few small collection of tricks which they have done, which makes this very neat. Like not just having sign as an activation, but they also make some small changes to the way they initialize the weights of the network. So we'll be looking at, let's first look at their official can you see the difference between the reconstruction of the video for SIREN and ReLU? The ReLU one seems to be a bit hazy, the SIREN one seems to be fairly good. Similarly, they do this for the audio also. Right. And this is not just applicable to audios, videos. They also have a nice TensorFlow playground fork that they have created. Now, the only change that you might be seeing here is that instead of other things, instead of the simple activation, they've also added a sine activation. Right. Let's go back to ReLU and see how the network is performing. It's fairly good, but it does take a few iterations. If you were to instead, let's make the model simpler. Right, this is with the ReLU activation. Now instead, let's use the sine activation with their set of weights that they're probably setting up. Right, that seems like a better fit. Not necessarily because you are also having some blue distributions here, but at least on the data that they have, it's been able to do much better job. This was a simple data. If we pick up slightly complicated data with the ReLU activations, okay, this might be too difficult with one hidden layer. Let's try with two hidden layers up to 200 odd iterations. It's not able to do a very good job. Let's move to the sine. Okay, here also for 200 iterations it's not been able to do anything well. And it seems to be stuck. Let's try and use a slightly more complicated network. Maybe decrease the learning rate a little bit. So it's been able to now capture quite good patterns. The training loss, test loss have both gone down. For about 500 iterations, the test loss is about 0.19. If you were to do the same thing with ReLU, okay, so for about the same number of iterations, it's quite stuck, right? So there is something magical going on. The details are left to you as an exercise to read. We will now come to the main part of this class, which is about implementing these things and understanding how coordinate networks may work. So then you can very directly apply this trick to your assignment. So I have downloaded an image of a dog, and as you may know, the image is containing, in this case it's containing 3 channels corresponding to RGB, and each of them is a number from 0 to 255, right? Currently it's an integer number. I will do a bit of pre-processing to min-max scale. The shape of the image at this point of time is 3 channels. The height and the width, 1365, right, the height and the width. So it's a wider image, and I will then move this to PyTorch so that I can use all the neural network like stuff. But this image may be too big for us to do anything significantly quickly. So I'll do a cropping of this image, and this crop will give us this roughly 400 by this, it will give us this exactly 400 by 400 patch, right? Now our task is, given certain pixels, like this is 1 pixel, x equal to 50, y equal to 50, and I know its corresponding pixel value. I want to be able to reconstruct the entire image in this way if I have a training data set like this. So I also move I have a 3 cross 400 cross 400 image, right? Now I want to be creating a coordinate data set from this. Let me first show you the output of this, and then we'll come on to what this function might have done. Okay, I had a 400 cross 400 image. I have converted that into an input and output pair. My input is this 160,000 rows of 2 columns, and my output is 160,000 rows and 3 columns. Right? So do we understand what is happening here? We take each of the 400 pixels here. Each of the 400 coordinates here, each of the 400 coordinates here. Totally we'll have 160,000 coordinates. So therefore our input is 160,000, right, comma 2, because each input corresponds to an X and a Y, and our corresponding output is a 3-channel output, right, RGB, right. So therefore we have input 160,000 comma 2 and output is 160,000 comma 3. I am just doing a bit of pre-processing, because if you look at the numbers, right, so they are as expected 0, 0, 1, 0, 2, 0, so on and so forth, right. That's the way I've created them. So they're going from 0 to 399 in each of the dimension, right. Typically neural networks don't work well with such ranges of numbers, so it's a good idea to convert them into some good scale. In this case, I will be making them into scale of -1 to 1. And I'm checking that the input output shapes remain the same. You can now see the ranges of values. So the x coordinate is now going from -1 to 1 and the y coordinate is also going from -1 to 1. Now my task is given pairs of images like this. So let me right. So given this input coordinates -1, -1, I want to predict 0.768, 0.768, 0.764. Given the next input -0.99, -1, I want to predict 0.76, 0.76, 0.76, right. So does this entire idea look like a very stupid idea to you? Why are we creating such a complicated, why are we trying to learn this network when we already have the data available in the form of a 2D matrix, 3D matrix, right? Can anyone think of this? Okay, so there are two motivations, at least two motivations we can think of. The first one being the meta learning setup, the meta learning or the few shot setup, where for a new task you have only a few pixels available, right? So therefore you need to have a coordinate map, which a function which maps from coordinates to pixels, right? If you just remember these words, a functional map which takes coordinates as inputs and gives pixels as outputs, right? Coordinates to pixels is the functional map that you're trying to learn. It's useful in the context of meta learning. Secondly, let's look at a hypothetical scenario. You are, let's say the internet at IIT Gandhinagar is failing for a specific day, right? They are doing some reboot, etc. They give you a very limited bandwidth of internet, but all of you have very powerful laptops, right? What can you do with coordinate networks now? You want to be transmitting images to your friends. Yes, sir.
Compress and decompress.
Yes, you want to be able to come. So let's say I can only transmit 1 megabyte of data, right? But my image is 5 megabytes, right? So what I'm saying is that I have enough compute and I'm sending to you, let's say I'm sending to Param, he also has a lot of compute. So instead of sending him the image, I will send him a neural network, or I will send him the weights of the neural network which have been trained on this specific image, right? So this neural network is a function which goes from coordinates to pixels. If I send that neural network to Param, and let's assume that that is lesser than 5 megabytes, that's only 1 megabyte, which is your bandwidth capacity for the day. So I send him that neural network. Now he can automatically, I also tell him that the size of the image is 400 cross 400. Now he feeds in these coordinate inputs and he's able to reconstruct the entire output, right? So this requires additional compute at my end, at his end, but assuming compute is cheaper, and in this case, we are able to reconstruct images this way over a bandwidth constrained network, right? What else could you do with such a network? You could do some kind of noise removal. Now, could you also do increasing the resolution? Could you increase the resolution this way? So currently my pixels, my coordinates are -1, -1, minus 0.995, -1. If I take another coordinate in between these two, minus 0.9975, right? I'll get 2x scaling, right? So I can increase the resolution of my image while just training my model on a very, while just sending my network, my model over the network. Right? You could repeatedly do this and you can get quite a lot of downscaling, upscaling that way. So the reason I said downscaling and then upscaling is that because in two different contexts, machine learning people typically call it increasing the resolution, whereas in earth sciences people typically call it downscaling. The same phenomena of increasing the resolution of an image. But is everyone now clear on the basic concept of a coordinate network? Right? So these are the coordinates. These are the pixels. For a grayscale image, we will have only one pixel value, right? And just to be very sure, you can also see the untransformed ones, right? Corresponding to 0, 0 and 1, 0, these are the pixel values. Right? Now, we will try and create a network around this, which is the coordinate network, taking the coordinates as input, giving the pixels as output. So my input is going to be x, y, and my output is RGB. Right? There is a bit of things I have done. First, let's just focus on the main part of the network. I have defined S to be the number of hidden units. My first layer needs to go from 2 to S, then S to S, S to S, S to S, then S to number of out. The number of out channels in this case is 3 because I have a 3-dimensional problem, 3-dimensional image. Right? Now I've made this code generic so that it can work with any activation function given. So I am giving the activation function. It could be a torch.sign, it could be torch.relu, anything you want to give. Right? So I am also giving number of out equal to 1. The default is 1. In this case, it's 3. And I am also giving something known as an activation scale. Right? So the activation scale and the specifics of the way I've initialized the weights. If you notice, self.fc1.weight .data.uniform. So it's a uniform between something and something, and for the other layers also it's a uniform between something and something. Right? There is a function of the activation scale. The specifics you can find in the paper. I am not going to go into that. But what I am saying is, if my activation is torch.sign, then I can use this method to initialize my weights. If it's relu, I just use the same method to initialize the weights of the network. And the forward, I am also multiplying my output that I am getting from a fully connected layer with some activation scale, which I have passed as an input to this model. Right? So nothing very sophisticated. The only thing is this few lines of code which is for initialization of the weights. Right? And instead of the relu, I can also give the sign as an activation. I am doing some standard tasks like shuffling the data set, etc. I'll be creating two neural networks, one corresponding to relu activation, the other corresponding to sign activation. And if you notice, I have kept the activation scale to 30. Again, this is recommended in their paper. Okay, I have not run this code. Now, as a sanity check, I always want to give the input and I want to ensure that the output sizes are the same. I'm getting something useful. So I give my entire input and I get my correct shape output 160,000, 3 for both the networks. I'll be training these networks for 2000 iterations. My train function is quite simple. I'm using the mean squared error as a loss because this is a regression problem now. I am using Adam as an optimizer. My output is the net of the inputs. Everything else is quite straightforward. The one important thing to catch here is my outputs would be n, 3 here. So my PyTorch function is automatically able to take outputs of n comma 3 and my y also of n comma 3 and able to give you the mean squared error. So if you've been following till now, what I have given is I have converted this image, this dog image, I have done a bit of pre-processing so that I can create a coordinate network, and I have then also done a min-max scaling on the coordinate network inputs. So this 400, 400, 3 image I have converted into my input x, which is a coordinate input, which is 160,000, 2 corresponding to x's and y's, and my corresponding output is pixel values is 160,000, 3. That is my input and output, and my neural network is trying to learn this functional mapping.
So you said in comma 3, so there are 3 output nodes for after the neural network.
Yes.
So you calculate loss for each of them, and is the total loss sum of all those?
So I think it may be just flattening them out.
So do we take the mean, or because we need the contribution of all the losses?
Yes, so it can just flatten out all the values into one large vector and then compute the mean square. You can check this at your own time. If you have multiple outputs and you directly pass it to the mean squared error, how is the functional mean mapping? So we run this for a few iterations. The loss on the training data set, which is the entire data set, is quite low. It seems to be 0.02, and then I want to reconstruct the original image from the neural network, right? So now I will be giving in the inputs, which is the coordinates, and I will want to see how well this is able to reconstruct. What happened? Do you like the reconstructed image? No, right? Now, one of the problems is that the loss numbers can be very misleading. The loss seems to be very low value, right? But you have to view it in the context of the task at hand. Here it's able to do, you can get some features, but not all. So I can show you some different variation of this, where I ran the similar kind of code a few months back, and I got slightly different answers. So it was maybe a different configuration of a neural network, different input initialization, etc. So in my earlier experiments, this was the image that I got from ReLU, and this is the reconstruction image which I got using the SIREN. So this one is probably better than what I am currently showing you, and this was the animation of the training process. Do you see that the ReLU one is trying to, like, it will not be able to do well, it's very clear, whereas the SIREN one is able to very nicely capture all the patterns. Coming back, now we do the same thing but for the SIREN network. So let's look at the numbers. At epoch 100 for the ReLU network, the loss was 0.03. At 100 epochs, the loss for the SIREN is 0.009. It's order of magnitude better. We have not changed much. We have just changed a little bit of the weights initialization and the activation. And the overall loss, if you see, it's gone down quite low. If we now plot the reconstruction, it's far better, right? It's still not perfect. So that's where we have a lot of scope of playing around with the parameters, hyperparameters, etc., like the learning rate as well as the number of neurons, the number of layers, etc. But essentially, we are able to do a much better job, which is enough for today's class to show that it's we can solve such problems. If we look at the test error, which is the reconstruction error, with the SIREN network we get at 0.002, whereas with ReLU it's 0.02. So an order of magnitude better with the SIREN activation. Now we come on to the task which we originally wanted to see. So currently I use the entire network to predict the entire image. I use the network trained on the entire image to predict the entire image. It's a bit of wasteful exercise, but we still needed to do. Next, I want to see if I am given a small context. I am not given the full image, but I am given some pixels in the image. Can I reconstruct the entire image? So therefore, I'll be looking into different kinds of context lengths, 5, 10, 100, 1000 and 10,000 and then the entire image. And for each of them, I will be creating a neural network corresponding to, and the important thing here is that I will be giving only the few subset of points, right. For context length equal to 5, I'll be only giving 5 pixels in the training. Again, don't get misled by the numbers. They may be looking very low, but you should be looking at the visual reconstruction to make a better sense of if the task has been successfully done or not. What do you notice from these numbers? As you increase the context size, the reconstruction accuracy becomes poorer, better, right? Which is quite expected because now you're giving in more images. And if you have to plot the reconstruction error with respect to the number of context points, we can quite clearly see the trend. Right? As we increase the number of context points, the reconstruction error will go down quite a lot. Right? Now you're free to make a lot of changes to this code, do various experiments, including you can try and increase the resolution of the image. You can also, currently in this context length, I have randomly picked up 5 images, 5 pixels. You could pick up patches. You could remove certain patches from the image and try and then fill that patch using this network. That patch could be a rectangular box in the image. It could be one half of the image missing. It could be a diagonal part of the image missing, so on. And now let's look at some of the reconstructed images. Okay. What do you see in the first network? Nothing, right? But the reconstruction loss was not very bad. At 10 points, again, you don't see 100 points. 1000 points, you start seeing some basic structure. 10,000 points, you can pretty much see the entire structure. With a slightly better network, maybe 10,000 points is more than enough, or maybe even 10 points is more than enough. At 16,000, you're able to quite well do this. Right? Now we come back to the question which I asked a few minutes back. We want to compare the network size. Like if we were to send this neural network over the network over the internet, let's call it the internet, versus sending the image over the internet, which would require more bandwidth. So I have done a comparison. If I have to send, this is the number of floating point values. If I have to send the image, my number of floating points is 160,000. Okay, this is actually wrong. It should be into 3, right? And my network size is the size of the neural network. So that is much smaller, right? So if you send this network, you will be saving a lot of some bandwidth, right? At the cost of a lot of additional computations, right? But one downside of this approach you might have already seen is that you need a network per image, right? Which is where meta learning comes into play. Can you learn something which is going to generalize across a lot of images, or can you learn a hyper network which can then predict the weights of a target network, where the target network is specifically designed for an image, right? So we looked at this in the previous class. Right, we looked at this setup where we're given a context set. This is NC, comma D plus 1. Why is it D plus 1? My input image is D-dimensional. My input is D-dimensional, and I'm also appending my Y to it. So my context set means the pairs of X and Y, which I know for every task, any given task. This goes into a hyper network. This produces a representation which is NC, because I passed in NC input objects, So this is NC cross K, and that I aggregate to a k-dimensional flattened out vector that I reshape into the weights and biases of a target network different layers. That now if I pass in any target set of points which is n comma d, not n comma d plus 1, I have a target network which is now specific to this inputs, and I can then get the corresponding outputs, right. So in this setup, in the image reconstruction problem that we are saying, we will have certain pixels which we are knowing, which go as a part of the context set, and then you can give everything, the coordinates for everything else in this part, which is the target part. The target net has to be defined by the context points. So you have to have a target net specific to every new task, right. So think of each, for every new image you will have a new target net, but you are getting the target net from this context set of points. I don't see a lot of happy faces. Doubts in this? Do you want me to repeat? Sorry? Target net. What is a target net? The target net is exactly what we have been doing thus far. So this network, so the current task which we have done till now is a target net, right. What does the target net take in this case? Coordinates, gives out pixels. Target net takes in coordinates, gives us pixels. But in this case we have learned a target net per image, right. But what we are now saying is that, can we have another additional network called the Hypernet, which gives us the weights of the target net, right. So my target net has these parameters. It has these parameters: FC1 weight, FC1 bias, FC2 weight, FC2 bias, FC3, so on and so forth, right. So what I am saying is that, can I learn these weights on a per image basis, right. That's the first thing you want to be able to do. Learn the target net, this is the target net, learn a target network on a per image basis. The way we do that is, we pass in a few context set of points to an additional network called the Hypernet, whose output is a flattened vector, a flat vector k, which we can then reshape to these weights and biases. Yes.
So are we trying to predict the weights for the target network?
We are essentially trying to predict the weights of the target network using a few context points available from the target task. Questions? Do you want me to ask questions? Okay, so let's see this in action on how we may go about doing this. So firstly, I wanted to create a nice looking table which counts the total number of parameters in this model, let's call this the target network, across the different layers, and let's imagine that at the end of the day, some network, somehow we got a flattened vector of size 50,307 parameters, right. I want to reshape them into 256 parameters which go into FC1 dot weight, 128 parameters numbers which go into FC1 dot bias, 16,384 parameters numbers which go into FC2 dot weight, and so on and so forth, right. So therefore I have shown this process of starting an end index corresponding to each layer's weights and biases, right. So out of the 50,307 parameters, somehow if we were able to get a flattened out vector corresponding to this, we can simply index from 0 to 256 and get FC1 dot weight, set FC1 dot weight, 256 to 384 set FC1 dot bias, and so on and so forth. This may be off by 1, but those things are minor things, you can change, correct those, right. So the task here at hand is, given a flattened vector of 50,307 numbers, I want to reshape them into these weights and biases for a target network, right. And I have done this by manually creating this index corresponding to each layer and each weight and bias in the layer, I have stored the start index and the end index. Something like this, right? Now, my hyper network will take x, y and RGB as input, right? X, y are the coordinates, RGB are the pixel values which I have from the context set of points, which is a small subset of the points I have for a new task, right? Given x, y, RGB, I want to predict, so this specific network, hyper network, will predict 50,307 numbers, right? So I have created this 5, 512, 512, 512, 512, total number of parameters, where total parameters is 50,307, right? And it's just a simple network, nothing sophisticated about it. I'm now doing a dummy task on this. I create this hypernet, move it to the device. I pass it some random inputs of size 10, 5. Let's say I have 10 context points available. If I get 10 context points available, each of dimension 5, if I pass it through my hyper network, what is the size of the output that I'll get? 1, 50,000, right? Or 10, 50,307. How many think it's 1, 50,000? 50,000. Okay, how many think it's 10, 50,000? So it's 10, 50,000 because the input image is, the input is of size 10, 5. Therefore, the output will be 10, 50,307. Right? That you have to then aggregate it to get a 50,307 vector, which is the same thing we discussed earlier. You get NC, K. NC is the number of context points cross K. K is the dimension of the representation that you've learned. Once you aggregate it over the number of context points, in this case, I'm just taking the mean, I will get a K dimensional vector. My K dimensional vector now is of size 50,307, right? So, if you were confused, you can think of starting from this point. You are given a few context points, which is X, Y, RGB. You pass it through a hyper network, which takes 5-dimensional input and gives you some vector of 50,307 values. You have to flatten it aggregate it and then flatten it. So, you get a 50,307 weight vector. Now, you can use a simple for loop and set the weights for the different layers, right, in the target net. So, my target net, I am just calling it the model, which is the SIREN network that I had, and I got the start and end from my mapping, which I had saved earlier. I am just setting the parent.data equal to weights flatten start to end reshape. Right. Again, these are some engineering tricks. You can do much better than this, and we'll show how to do better than this.
So what was K?
K is 50,307 in this case.
So like what K represents?
K is the flattened vector, which if you unflatten, you will be able to get the weights and biases for the different networks, for the target network.
So we are passing 10 context points.
You are passing in 10 context points. So, therefore, you will get a matrix of 10, 50,307. If you had instead passed in 20 context points, you would have got 20, 50307. So, I get the question that he was trying to ask, but he is not yet asked. So, his question was, why not use the entire 10, 50307 points, right? We can't use that because we can have a variable context length. Therefore, we have to aggregate over the context dimension. So, therefore, we'll have to aggregate from 10, 50,307 numbers to something which is 50,307 numbers.
Aggregate means the all dot mean.
No, target here means the target network.
Aggregate.
I've done the mean over it. I've done the mean over the context dimension. You can see the entire code. Output from the hyper network is the hyper network whose input is the 10, 5. And the output I am getting is 10, 50,000. I then flatten it out. Sorry, I take the mean over the first dimension. The first dimension was the context dimension. So, I get a vector of size 50,307. Other questions?
Context points from a single image.
The context points are from a single image.
So why do we have two networks? Why can we not just use the target network?
Right. Okay. Does anyone want to answer Aditi's question? Why do we have two networks? Why can't we use a single network? A little louder. Right. So let's imagine the case where we use only the 10 context points as an input, right? So you have only 10 inputs and you're trying to generalize the entire image, right? So from the new task at hand, you have very few examples. So you'll be able to do not a very good job, right? So previously when we had only 10 inputs, see what we got. Right? The reconstruction was poor, right? What we are saying is that in the meta learning setup, can we learn a network which can better predict the weights of a network which is the target network? So it's a meta setup, right? Given a few context points, can we reconstruct the weights of a network which can then very accurately reconstruct an image? Yes?
We're trying to reduce the number of context points.
We will be typically given very few context points. So that is the setup. Therefore, it's few shot learning. We will never have, so we will assume that we don't have a context, we don't have a lot of context from a new task at hand. So therefore, you want to be somehow still be able to leverage the data which you have from other tasks, right? So one way to do that is to assume each task to be independent, which is what we did here. This task was an independent task. I had 10 context points. This is my reconstruction. It will be poor. The other end is let's think of the other end of the spectrum, similar to the FVC example that we had. You give X, Y as an input. Now you're trying to reconstruct all possible images. Will it be a good reconstruction? No? Yes? So let me repeat my question. Okay, let me actually show you what I meant. Okay, what do you see? Grass, I mean nothing sophisticated. You see another image, right? Now let's look at a single network which takes coordinates x and y and tries to predict the pixel values for all the images in the world. So if I have a single network which tries to predict at, let's take very specific values, it will become very clear. Let me convert this to also dog x crop 2, dog y crop 2, crop 1, crop 2, crop 2. Okay, good. How many of you are facing this error for the previous week? No notebook document. Like this is a documented error recently happening with VS Code. I hope that my changes will resurface when I okay, but I'll have to restart the notebook now. So we can very clearly see that crop 2 is very different from crop. Right? So for the first image, pixel values goes into networks, coordinate goes into a network, out comes the pixel values. 0, 0 goes into the network, out comes 0.67, 0.67, 0.67. Let's do the same for the next image. 0, 0 goes in the input as an input to the network, out comes 0.9, 0.9, 0.9. Now, if you feed in all the data in a big folder, you're trying to learn a single network which will, given the coordinates, reconstruct an image. Will you be able to do a good job? No, right? So we have looked at two extremes. Can someone help us with the two extremes? What is the one extreme we are currently talking about, Vipul? So we have two extremes in which we can do such modeling tasks, right? The first extreme, okay, someone else wants to try this? Okay, Ritik.
First extreme is to learn a different network per image.
Okay, one extreme is to learn a separate network per image, or you're learning a separate function per task. Or in the previous example which we discussed 2 weeks back, we are trying to learn a function, we are trying to learn a separate function between weeks and a person's lung health, right? What is the downside of that?
The moment the new test data comes, everything goes.
Okay, one, it's not going to work very well for new data, but there are other problems. Sachin? We have very less data for a patient, which can lead to high variance, right? Overfitting, and you'll also have high errors. You can also have high uncertainty, right? So this is one extreme where you're learning a function specifically for a new task. So function per task, right? The other extreme, sorry, completely pooled, where you have a single function for all the tasks, right? That corresponds to, I have a single network which takes the coordinate 0, 0, and it is trying to predict the pixel values corresponding to all the images in the world. That will not work at all. That will be probably just give you a blob of the data which works across reasonably well across a lot of data images that you have, right? So therefore we need to have something in between which is not as specific as one task, one function per task, or it's not as poor as one function for all the tasks, right? So therefore we come up with a scheme like this. We have the meta input or the context, which will be a very few set of points available for any task, which goes into a hypernetwork, which gives us the weight for the target network. The inputs will, so this is the network which will accept coordinates as inputs, give pixels as output. Coordinate to pixel network or the coordinate network, whereas the meta input is the goes to the hypernetwork. The meta input in this case is xy, RGB, and that sets the weight for the target network. Right? Okay. Other questions? So this is the main thing they have showed in a couple of such papers, that it's usually useful to do this meta learning setup rather than learning on something on a per task basis. So we can, in this paper they are actually comparing the neural process with the hypernetwork, etc. And since this was the first neural process paper, so they were looking into this meta learning setup. So they didn't have to compare against those previous works. Okay. So then when you're practically trying to implement this, you would have to create a hypernetwork, right? In this case, the hypernetwork takes in XY RGB, gives some big number, 50,307, right? So therefore, first, when you're thinking about this, you have to create the target network, figure out the number of parameters for that, then create the hypernetwork whose output should be the number of parameters in the target network, right? The input to the hypernetwork is the context size, which is in this case xy as the coordinates and RGB as the pixel values. And this small example should be telling you exactly what it does. creates a new hypernet, 10 context points of size 5 XY RGB, creates 10, 50,307 matrix. You aggregate it over the context points, you get a vector of length 50,307. Now somehow you want to put these 50,307 numbers into this network, into your target network, right? So I have done some bit of maths, some bit of simple for loops for you so that you can reuse this code. This goes from 0 to 256, 256 to 384. You'll have to be a little careful with the indexing, like 0 indexing, 1 indexing, so on. So then you can set the weights via some kind of code like this, right? I have not fully tested the code beyond this. So you'll have to make functional call and then be able to do something more than this. But that I had already shown in this notebook. Right, the complete forward pass I had shown in this on multiple tasks I had shown on this. So I will not talk about in this in today's class. But I also wanted to show you that. So here I had to write this for loop myself, right, which is now prone to error. In the tree-like world, so there are quite a few libraries these days which operate on these tree-like data structures or nested dictionary-like data structures. And our lab has also been working on some such tools. So you can look at the repository for the lab. This is the specific bunch of tools. So I want to show one specific tool which is known as Ravel PyTree. This has been inspired by something which exists in the JAX world. Right? So let's look at what this function is trying to do. I get flat weights, comma unravel function, which this function is supposed to take a flat vector and put it back into a specific shape, into specific dictionary like shape. So I called Ravel PyTree on dict of model dot named parameters. So firstly let's see what dictionary of model dot named parameter gives you. Okay, not. Oh, I had to run this notebook again. Right. So if you run a dictionary, if you create a dictionary of the model's named parameters, you get the keys corresponding to weights or biases and the corresponding tensors, right? So this is a nested structure. So given this nested structure, you are trying to now create a flattened vector, plus you are trying to create a function which can take you back from the flattened vector to this dictionary structure. So this unravel function is that function which goes from flat to a PyTree definition. Right. So first let me show you the Ravel PyTree function. It took that dictionary, nested dictionary, and it gave you a 50,307 parameter. Right. Now you can take this unravel function, right? You take this unravel function on the flattened weights, which is a vector of length 50,307, and what do you get? Right? You now get the dictionary which is of the exact shape, exact nested structure which you wanted. Yes. Sorry? Which means? This function will take care of. And you can look into the code, source code of this function. You can, should be probably in utils.
So we have parsed the model and in the argument also.
Okay, what is the question?
I was saying we have passed the model as an argument also.
As an argument also.
model dot name parameters.
So let's, in order to reduce your confusion, let me, so you get a dictionary, let's call this nested dictionary of weights and biases, right? And now to Ravel pi tree, you're passing a nested dictionary of weights and biases. Okay. Given a nested dictionary of weights and biases, you can conveniently flatten them using this function. And then you also need a function which goes from a flat structure back to the nested dictionary structure, right? That this functionality, this function is giving you, and therefore if you were to call this unravel function on the flat weights, you get the exact same structure, right? If you want, you can also add some asserts to check whether this is correctly working or not. The way we will be using this is, we will actually come here, right? We would have created a Hypernet. For that Hypernet, we would have passed some set of context points. We would get the flattened weights, right? We can view the flattened shapes, and then we can unravel, call the unravel function on these flattened weights, which we are getting from the Hypernet's output, and voila, we have a no notebook document found. So we have then got the weights corresponding to the network. Now you can easily make a functional call in PyTorch, and you should be able to accurately get, and you should be conveniently able to get the weights and biases corresponding to the new target network, right? So if you are not going to use this specific technique, you would have to write loops like what I had written here, right? You will have to first create an index of the starting and the end position corresponding to that weights and biases, and then you would have to set the parameters like this, right, by indexing from start to end, which is prone to errors, whereas this specific functionality will make your life much simpler. And then we have also created some utilities along this SIREN, creating these SIREN networks. So if you noted that we had to create quite a few amount of modifications to the original network, right? So we had to do a little bit of manipulation about the weights of the network, as well as how the forward pass happens, etc., right? So we've again given you such functions in this library, so that you can very conveniently create a SIREN-like network, right? Input dimension is 2, output dimension is 3, so it's a coordinate network going from 2 to 3. The hidden dimensions are 256, 256, 256. You can create this network S. You can also then call a train function which accepts a model, inputs, output, loss function, learning rate, number of epochs, etc. So if you're given some convenience wrappers, this should hopefully be useful for your assignments. Questions? I think now you should definitely start the assignment, because you may have seen that this is not very trivial but not very difficult also. Like now in the assignment, all you need to do is to take whatever code I have written for the Hypernet as well as for the target net and link them up in a forward pass, so that you are able to back propagate the gradients towards the Hypernet. I had already shown that in a previous notebook, Hypernet neural process.ipynb notebook, but I am not showing it specifically here because otherwise I have solved the assignment for you. Okay, questions? Okay, Vipul asked a question about, so this question in a slightly different form was also asked in the block 7 classroom when we had this class. How do you decide the number of context points? Is there a particular schedule you give to context points? So you will have to just try it out. There's no as such very good recipe that I know. Right? Typically, you don't want to be giving a lot of context, because in your target task, you also don't have a lot of context at hand. You can fix the context length, but in each iteration you can pick up a so that's how typically this setup would work. In each iteration of training, you would take the training data, and some of which you would keep for as context, some of which you would assume to be target. You always split that.
So here we're passing context independent of each other. So every part is independent, predicts, let's say predicts what the image should be independently of the other context. We are not leveraging, like there are 2 points, we are not leveraging, okay, we have a point there, so this would have predicted something else.
Okay, so I'm not fully getting your question, but given a context, we will try and see what is the best set of weights for that specific network. That is the background. Now let's come back to your question. Can you repeat?
We have 10 context points, 100 or 1000 context points. Every context point predicts a different neural network. Or let's say if we go back, not the neural network, we're talking about we have created a network that predicts the image itself. Earlier setup. If I pass one context point,
Okay, let's go back. Let's do one thing at a time. Are you talking about the coordinate network?
the coordinate net.
Coordinate network. Okay, let's go back to the coordinate net.
I pass one context point or 10 context points.
So you pass in this, you are not passing in the context points as per the strict definition. You are passing in coordinates x and y, and you're getting in the pixels, right? Okay, now your question. In the target net, you will be giving in target net takes in the input, the hypernet takes in the meta input, or target net is n cross d, context set is n cross d plus 3 in this case.
What my point was, we are passing context independently. They are not able to leverage what the other point has or what the.
So in the target net, we are not even passing in the context, right? So if you're talking about the first setup, which is the reconstruction problem that I have done, there is no context. There is just coordinate input, and I get the pixel output. So therefore, it's a coordinate multi-layer perceptron with a sign activation. Only when we talk about multiple tasks, meta learning setup, we introduce the context set, and we divide the training data into context and target, and then we pass some of it to the hyper network to try and learn the weights, which should be able to nicely reconstruct the given the coordinate the pixel values, right? So let's look at this flow again. Let's take this image as an example, right? You have 100 context points, right? So therefore your context input size is 100 comma 5, right? X, Y, R, G, B. Your coordinate, your input to the hyper network or to the meta input, the input that you're giving is 100 comma 5. That will lead you to, and what you're saying is that let's imagine that this is a part of the training phase, not testing phase, right? During training, let's imagine that 100 points you're setting as context. The remaining whatever number of points, let's say 50,000 points, you are feeding it. The remaining 50,000 points you're feeding into the input, right? In the next iteration, maybe you'll pick up a different set of 100 context points, a different set of remaining points, and then you're trying to see, given this context, what does my network learn so that it's able to accurately reconstruct the pixel values for a given coordinates. Okay, other questions? Little louder. You are doing across multiple images, across different iterations. No, you can. So this whole setup you can do across. That's the whole point. You want to do it across multiple images, right? Sorry. MNIST. celeb. Like that's the question. If you look at the assignment question, use your own version of the following models to reproduce figure 4 from the paper. And this is the figure 4. Right? You have 60,000 images in MNest. You can use those images, and for every target image, right, you can divide the context and train, and then you can try and predict from the context you're trying to predict for the remaining images. So I think there are few concepts that we studied today. I had earlier planned to discuss active learning also today, but I think there's no point. Let's try and review the points which we've discussed today. Firstly, we looked at coordinate networks, right? So this line is pretty much telling what coordinate network is. Coordinate network is a network which maps from pixel coordinates to pixel brightness, right? In certain cases, pixel brightness would be RGB. In MNest, it would be grayscale, it would be single output. In the celeb, it would be RGB, 3-dimensional output, right? So this is a network that we chose. Second, we looked at such a network could have ReLU as an activation, it could have a sign as an activation, any activation. What we looked at is if we follow this paper, SIREN paper, and if we carefully initialize certain weights, right, as per what they have mentioned in this paper, if you carefully initialize some weights, we are very nicely able to reconstruct such images from this coordinate networks. Right? Thus far, we are just talking about a coordinate network, which you can also think of as a target network. Right? Now, we are trying to learn this f from pixel coordinate to pixel brightness as a regression task. You can very carefully see here, x0, x1 are the pixel coordinates, and correspondingly we have the pixel brightness. In this case, it's a one-dimensional problem. So we are trying to learn this as a regression problem in this 2D space. Right? Now we have looked at the coordinate network, we have looked at SIREN as the modeling framework, sign as an activation, and with a specific set of initialization. And we have understood how this network would perform, how the reconstruction might happen. So we looked at this notebook. We saw that with a ReLU based network, we are not able to reconstruct very nicely, whereas with a sign based network, the reconstruction is far better. Then we took on this problem of, let's imagine that for this specific problem at hand, for this reconstruction problem, I had very few set of points available. Right? And if I had very few set of points available, it's very clear that as I increase the number of points which I have available, the reconstruction would become better. Right? But at this point, we said that there are two extremes of this problem. So this is essentially a few shot learning problem that we are trying to solve, or the meta learning problem that we are trying to solve. We have two extremes of this problem. The first one being that we learn a single function f, which maps from pixel coordinates to pixel brightness for any image in the world. Right? It will do a very poor job. It is the pooled model. On the other extreme, we have a network per image, which will work well for that image if you have enough number of inputs pixel coordinates available. That is what we have seen. If you have enough of these pixel coordinates available, you would be able to do quite a good job. But typically, you may not have a lot of such context points or labeled points available from a new task at hand. Right? So therefore, we can't also learn a separate model per task. This is where the meta learning setup comes in. In the meta learning setup, what we are trying to say is that we want to learn two networks. Essentially, we want to learn one network, which is the hyper network. We give it the meta input or some context points, some labeled points. In this specific problem, it's xy, which is the coordinates, comma RGB, which is the pixel intensities. These go as input to the hyper network. We then predict the weights of a target network. Into this target network, we pass in our coordinate inputs xy, and we predict the RGB values. We know the ground truth RGB values. We can compute a loss. We can then back propagate and update the gradients of the hypernetwork. So we are always using the hypernetwork to set the weights of the target network. So we looked at this. This is the hypernetwork way of solving this problem. This is a slightly harder way, in my opinion, compared to the other way which we saw, other variant which we saw, which was neural processes. Although we are not looking at the processes part of it, we are only looking at the encoder decoder architecture of it, where what we showed was we'd again have a similar setup. We'd have a context set which is nc comma d plus the number of y values that you have, in this case nc cross d plus 3. That goes to an encoder. It gives you a representation of nc comma nc cross k. You will aggregate it to 1 cross k. Thus far everything seems to be similar to what we have done, but now we are not setting the k as the weights of the different network, but rather we have a decoder which takes in the train input as well as the features which we have learned, right. So we have an n cross d input and we have a 1 cross k features. We concatenate them into the enhanced features which is n comma d plus k features. We have k additional features which you have learned via the encoder. That goes into the decoder, which then produces, in our case, it will produce the 3 values RGB, y hat, and then we have the y true, and from that we have the loss. In this network, we will back propagate to both the decoder as well as the encoder. Whereas in the previous setup, in the Hypernet setup, we were only back propagating towards the hypernetwork, right. So therefore, there are 2 variants of this problem. Yes. Here k is a hyperparameter. So in the previous case, we had to set k specifically to match the target network. Here k is a hyperparameter about the representation length which you choose or the embedding length that you choose, right. You can use both these networks. We have given the code for both these. For using both these networks, you can try and solve the meta learning problem. Right. So again, coming back to the main objective, for the previous 3-4 classes, we've been stuck to this objective. We have very few data for a new target task at hand, right. We could use things like hierarchical models, Bayesian hierarchical models, where we are trying to somehow capture the dependencies amongst the different tasks. That was one method. Then we looked at the neural process or the encoder decoder architecture for the meta learning. We also looked at the hypernetwork architecture, and today we looked at a very specific application of image reconstruction, which is one of the questions in the assignment. So thus far we have understood some methods of predicting in the few shot setting when we don't have a lot of target points available, a lot of data available from the target task at hand, right. That's few shot learning. In the next few classes, we look at other variants of trying to solve this problem when we don't have a lot of data available, lot of labeled data available from a target task. One of which is called active learning, where we'll say that let's strategically try and curate a larger training data set for any task at hand. That's one. Second, we'll be looking at some methods of self-supervised learning, where we say that let's leverage all the large unlabeled data that we have, and let's look at some pre-training like tasks, like what GPT does, what BERT does, those methods. So all of them are mainly still just guided along the few shot, 0 shot kind of problem set. Okay, I will end here. Any questions?
How do we connect this to probabilistic?
So we connect this to probabilistic because we are not, I think the general confusion comes in when we think of probabilistic as Bayesian. So this course is probabilistic ML and not Bayesian ML. Right, so you're probably missing, this is not a Bayesian method of doing that, but it's a probabilistic method. Right, so I think to some extent even I was generally in the mindset of probabilistic and Bayesian, think of them as more or less equivalent, but they're not. You can have frequentist method which are probabilistic. Okay, thank you.